Okay students, let us try to solve this question. How much energy is required to ionize hydrogen atom if the electron occupies fifth orbit? Okay, we need to find out how much ionization energy is required to remove the electron from the fifth orbit, and they are asking us to compare with the ionization energy of hydrogen atom where the energy required to remove the electron is from first orbit. Okay, so we need to first find out the energy required in the fifth orbit, and then the ionization energy required to remove the electron from the first orbit, and then compare. Okay, so let us solve this. We are aware that the energy formula which we are having is written as minus 2.18 into 10 to the power of minus 18 divided by n square joules per atom. This is the formula for the nth orbit. Now here n, which we have written in the denominator, is the orbit. Now here what they are saying is your electron is in the fifth orbit and it is to remove what amount of energy is required to remove this electron. That is referred to as ionization enthalpy. Okay, so first for ionization from fifth orbit, where your initial level would definitely be 5, and as the electron is removed from the fifth orbit to somewhere else above it, so we take that as n final as your infinity. Okay, so electron is removed from the fifth orbit, where I, that is initial orbit we are having, is orbit number 5, and it is somewhere going away from it, so finally we have taken it as infinity. So therefore now we are knowing the formula for energy for various level as E is equal to minus 2.18 into 10 to the power of minus 18 divided by n square. Now let us try to find out the change in enthalpy, ionization enthalpy, which will be written as E final minus E initial. So E final will be where n square would be 5 square, infinity square, and E initial would be where I would be your 5 square. So how do we write this? We can write this as, we can take out in this minus 2.18 into 10 to the power of minus 18, we can take out common, and then we have final nf square minus ni square. So I just now told you that your 2.18 into 10 to the power of minus 18, nf would be infinity square minus initial is 5, so 5 square. So now 2.18 into 10 to the power of minus 18, now 1 by infinity is 0 minus 1 by 25, so you end up in 2.18 into 10 to the power of minus 18 into minus 1 by 25. So you divide 2.18 with 25, you get this value 0.0872 into 10 to the power of minus 18. This minus will be becoming plus. Now let us shift this decimal point which you are having here between 8 and 7. So on shifting, you shift towards right by 2 digits, 1, 2, therefore it would be 10 to the power of minus 2. So 8.72 into 10 to the power of minus 2, because we have shifted 2 digits, and 10 to the power of minus 18 you are already having. So answer finally comes out to be 8.72 into 10 to the power of minus 20 joules. This is the ionization enthalpy of the fifth orbit. Now we have also to find out the ionization energy required to remove an electron from the first orbit. So now for first orbit, for ionization from first orbit, So there your orbit initially is your 1 and your final orbit is your infinity, because ionization is taking place from first. So then let us try to find out the change in the similar manner. Let me write the difference of energies as delta E naught. So that would be E final minus E initial energies. Now minus 2.18 into 10 to the power of minus 18, we can take common. We are using this formula which I told you in the beginning, this formula of energy we are using for both EF and EI. So in both, minus 2.18 into 10 to the power of minus 18 can be taken common. So that I have taken common, and then we take 1 by infinity, that is your final square minus your initial square. As we have done here above, same formula we are using it, but the levels are changing. Here we have first level. So this would be 2.18 into 10 to the power of minus 18. 1 by infinity is 0 minus 1. So here you will see that you end up in value of minus 1, which will finally become plus 2.18 into 10 to the power of minus 18 joules. That is the ionization enthalpy or energy required to remove an electron from your first orbit. Okay, now let's compare. As they are asking, you need to compare. See, the question was compare your answer, and that's why we had to find out the energy required to remove an electron from the first orbit. Now how do we compare? We just take both the energies which we have just now got, delta E naught and delta E. So delta E naught I have found out 2.18 into 10 to the power of minus 18, and delta E is 8.72 into 10 to the power of 20. So 8.272 it is. Okay, it is 72. Fine. So let me take this as 8.72 into 10 to the power of minus 20. Okay. Further solving this, you will see that 18 gets cancelled. You are left over with 10 to the power of minus 2 in the denominator, and you divide this 2.18 by 8.72, you will get 0.25, and this 10 to the power of 2 which is there in the denominator will go into the numerator as 10 to the power of 2. So final answer which you will be getting will be 25. Okay, so what they are telling, delta E naught divided by delta E is 25. So here delta, we can just write delta E naught, which we have taken as the energy to ionize the electron from the first orbit, is nothing but 25 delta E. Now delta E is ionization enthalpy of the fifth orbit. So this is your final answer. And how do we read this, or how do we understand? It's like the energy required to remove, thus the energy required to remove an electron to remove electron from first orbit. E naught was the energy of the first orbit. It is, you can see, is 25. It is 25 times than that required to remove electron from fifth orbit. Okay, students, even otherwise in your theory you have studied that if this is your nucleus and your electron is in the first orbit, and if your electron is in the fifth orbit, so it is, this electron is tightly bound to the nucleus. So definitely if we compare the energy required to remove from this orbit and from this orbit, so it is obvious that energy required to remove an electron from the first orbit would be more than the other ones. So I hope you have understood this final E naught, E dash is equal to 25 times delta E, means that the energy required to remove an electron from the first orbit is 25 times more than that is required from the fifth orbit. So this was the complete question which was asked. So we have first found out the energy for fifth orbit, then ionization for the first orbit, and then we have compared, and I hope you have understood. Thank you all.